picking up good vibrations.
In this video, we start with a small challenge for you. Can we express a periodic discrete time signal as a weighted sum of sines and cosines plus a constant term? To answer this challenge, we'll have to analyze carefully the class of periodic discrete time signals. And our findings will lead to the discrete time Fourier series. Have you thought about the answer to this question? Can we express a periodic discrete time signal as a weighted sum of sines and cosines plus a constant term? I hope your answers coincide with mine. Before going to that, I want to remind you that for continuous time signals, the answer is yes, but we need an infinite number of sines and cosines. In continuous time, we can replace the cosines and sines by complex exponentials. So also here, we can rephrase our question to, can we express a periodic discrete time signal as a weighted sum of complex exponentials? The answer turns out to be yes. However, differently from the continuous time case, we only need a finite number of complex exponentials, and in this video we start by discussing why by analyzing periodic discrete time signals.
The first crucial fact is that not all the cosines and sines in discrete time are periodic. In continuous time, all the signals of the form sine of omega t are periodic, as illustrated in this animation. For instance, if we choose omega to be 1, the period capital N is 2 pi. If we choose omega to be 2 pi, the period is 1. So the period in continuous time can be a natural number, but can also be a rational or even irrational number. However, in discrete time, the period must be an integer. If we simply pick sine of n, as shown in the top figure, we do not get a periodic signal. If we choose instead sine of 2 pi over 5n, we get a periodic signal with a period of 5, as shown on the bottom figure. You can indeed check that this new signal repeats itself every 5 samples. We can conclude that in general, a signal taking the form sine omega d n is periodic if and only if omega d takes the form 2 pi k over capital N for some integer k and positive integer capital N. The period is capital N. Let us plot for an example, considering capital N equals 5, the signals that we obtain as we increase k. For k equals 0, we have a constant signal equal to 0. For k equals 1, we have the so-called first harmonic, k equals 2 the second harmonic, k equals 3 the third harmonic, and k equals 4 the fourth harmonic. But we see that for k equals 5, we get the same signal as for k equals 0. For k equals 6, we get the same as for k equals 1. For k equals 7, we get the same as for k equals 2. For k equals 8, we get the same as for k equals 3. And k equals 9, we get the same as for k equals 4. When k equals 10, we go back to the same signal as in the case of k equals 0. Then for k equals 11, we get the same as k equals 1, and so on. We conclude that there are only 5 signals from k equals 0 until capital N minus 1, which is 4, and afterwards these signals are repeated for larger k. This conclusion can also be illustrated through an example. If we have sine of 2 pi over 5 times 6n, we can write it as sine of 2 pi over 5 times n plus 2 pi, which as we know is equal to sine of 2 pi over 5 times n. The same would hold if we had considered cosines instead of sines. The same conclusion can also be reached for complex exponential functions, that is, a complex exponential taking the form exponential of j 2 pi kn over capital N is periodic with period capital N, and there are only a finite number of different signals capital N in this class. This is illustrated in this example where capital N equals 5, and the real and imaginary parts of the complex exponentials are plotted. Note that indeed, both the real and imaginary parts are periodic functions, and the periodic plotted signals repeat themselves as k increases. This follows from the fact that a complex exponential is nothing more than a weighted sum of a cosine and a sine, and we know already that these repeat themselves as k increases. Since there are only capital N different signals in this class, it would be redundant to consider a sum of more than capital N signals. By convention, we consider the signals corresponding to k equals 0 until capital N minus 1, these capital N signals. Given an arbitrary periodic signal, can we then write it as a linear combination of these capital N complex exponentials? In other words, can we find the coefficients ak, the multipliers of these capital N complex exponential signals, so that when we multiply these complex exponentials by ak and then add the resulting weighted complex exponentials, we get the original signal? The answer is yes. To obtain the coefficients ak, we just need to solve a linear system with capital N unknowns, a0, a1, until a capital N minus 1, and capital N equations. The capital N equations are obtained by evaluating this formula, which must hold for every n, for n equals 0, 1, 2, until capital N minus 1. Note that x of n is known and given, and once we replace n by 0 or 1 or 2, also the complex exponentials on the right-hand side of these equations are given. The only unknowns are then the ak's, where k goes from 0 until capital N minus 1. If we can indeed get capital N equations from this method, we can then obtain these n capital N unknowns. Let us illustrate this for an example where capital N equals 4. Let us start by rewriting equations for capital N equals 4. As we have seen, this equation holds for any n, and what we'll do is to evaluate this equation for n equals 0, 1, 2, and 3. Let us start with n equals 0. Simply replace on the left-hand side and right-hand side n by 0. On the left, we get x0, which is given and known. On the right-hand side, we get a0 e to the power of j times 0, which is 1. And all the coefficients that multiply the ak's are e to the power of j0, which are 1. So we simply get x0 equals a0 plus a1 plus a2 plus a3. Let us now replace n by 1. Again, on the left-hand side, we get x1, which is given to us. On the right-hand side, we get a0 times e to the power of j0, which is 1, plus a1 times the given coefficient, now it's not 1 anymore, plus a2 times the given coefficient, plus a3 times the given coefficient. And these coefficients are complex, there's no problem. Let's continue this, and let's now write the equation for n equals 2. Again, on the left-hand side, we get a known value. On the right-hand side, we get a0 times e to the power of j 2 pi over 4 times 0 times 2, which is 0, so e to the power of 0, which is 1, and then we get some coefficient that multiply a1, a2, and 3, which are simplified here. Finally, for n equals 3, on the left-hand side, we get a known value. On the right-hand side, we get a0 times 1 plus a1 times the given coefficient plus a2 times the given coefficient plus a3 times the given coefficient that we can now write in a simplified formula and get these 4 equations with 4 unknowns. Now, to solve this, there are many methods. For instance, the Gauss-Seidel method. You can use whichever method you want. But at the end of the day, this is nothing more than a linear system of equations. We can write it in a matrix form as a vector x0, x1, x2, x3, which is known, equals a matrix times the unknown, and we can, for instance, invert this matrix and write a closed form expression for the a0, a1, a2, and a3.
We now have an answer to the challenge that we started with. Yes, we can express a periodic signal as a weighted sum of complex exponentials. Now, the coefficients ak that multiply these complex exponentials, we can get them by solving a linear system. However, there are also alternative formulas to compute these ak's, which are written here. The derivation of these formulas is given in lecture notes. Here, I just want to highlight that to compute the ak's through these formulas, you only need to consider the signal over a period from time n equals 0 until capital N minus 1. And then you compute also capital N Fourier coefficients ak.